Hello everybody, welcome into another lesson. Today we are going to talk about prime factorization of numbers, which is going to be a critical skill to use when we go to find greatest common factors and least common multiples of numbers. And when we go to factor numbers too, we're going to need it. And prime factorization involves what we talked about yesterday, exponents and powers. It does come into play into that. So before we get started doing prime factorizations, let's talk about different types of numbers. If we recall from basic math, when you have a prime number, it's a number that's only one in itself as a factor. Those are the only factors for the number, are one in itself. Then you have composite numbers where you could have more than one in itself, such as 21, where you have not only 1 and 21, but 3 and 7 as factors. If it has more than one in itself as a factor, it's a composite number. And then you have two numbers that are neither. 0 and 1 are neither prime nor composite. They're just their own. So that's how that works. The idea behind prime factorization of numbers are you want to get it down to a product of prime numbers. That's the idea. So let's go ahead, let's get started with our first example here. Say we have 26, right? 26, the prime factorization works on composite numbers. If it's a prime number, it's just one in itself, so prime factorization won't work on that. But 26, besides 1 and 26, you have 13 and 2. You got 13 and you got 2. As factors, when you multiply them together, you get 26. Can we factor 13 any further? No, it would just be 1 and 13. It's a prime number. Can we factor 2 any further? No, it'd just be 1 and 2. That would just be a prime number. So your prime factorization is going to be 13 times 2. And that's all you would get. That would be your prime factorization of 26. It would just be 13 times 2. Because they're both prime number factors of each other. Alright. How about 81? So we have 81 here, right? 81's definitely a composite number. It's got several factors besides 1 and 81. So let's start with 9 and 9. 9 times 9 is probably our greatest examples of factors, right? Can we factor the 9's any further? We certainly can. 9 can break down into 3 times 3. And then this 9 will also break into 3 times 3. So what you have here, you have the prime factorization of 3 times 3 times 3 times 3. Because if you go to where it stops being able to factor, you can't factor 3 any further. You just have 3 times 3 times 3 times 3. Or simply you could say 3 to the 4th is the prime factorization of 81. Now, prime factorization guarantees you're going to get the same prime factorization no matter what factors you choose to work with. So let's pick some different factors of 81 that I know will work. How about 27 and 3? We could do 27 and 3 because 27 times 3 is 81 also. Okay, we can't factor that 3 any further, but we could certainly factor 27. 27 goes into 9 and 3, right? We can't factor this 3 any further, but we can factor the 9 further. 9 breaks down into 3 and 3. So now, wherever you see the ends being just the prime numbers of 3, you take each of those as your factor, you multiply them by each other, you'll have 3 times 3 times 3 times 3, or simply 3 to the 4th. So This proves that no matter what factors you decide to start with, it's going to break down into the same prime number factorization. Alright? This is very useful, and it makes factoring actually a lot easier instead of just trying to pick factors and guess and try to do half of factors to make it work. Prime factorization will set you straight every time. Alright, how about 66? Let's do 66. Well, what factors of 66 do we have? The greatest examples we'd come up with are 11 and 6, right? Because 11 times 6 is 66. Can we factor 11 any further? No, because it's a prime number. 11 only has a factor of 1 in itself. We can't go any further with 11, but we could certainly go further with 6. Factors of 6 are 3 and 2. Now, can we go any further with the 3 or the 2? Can't go any further with either of them because they're both prime numbers. So your prime factorization is going to be equal to that 11, because that's a prime number, times that 3, that's a prime number, times 2. So your prime factorization is 11 times 3 times 2. Wherever you see the ends of the number tree that you can't factor any further, those are your prime factors. Okay? So yeah, 66, you'd have 11 times 3 times 2. Alright, then we got 63. Let's say we decide we're going to factor 63. Well, some great factors we know are 7 and 9. 7 and 9 are certainly factors of 63. There's others, but these are probably the simplest to work with. Can we factor 7 any further? No, that's a prime number, so it's just 1 in itself. We can't do anything further with 7, but we could certainly do something further with 9. 3 and 3 are factors. Can we do anything further with the 3s? We can't do anything further with them because they're both prime numbers. Both 3s are prime numbers, so therefore your prime factorization is 7 times 3 times 3. Or if you want to simplify that, it would be 7 times 3 squared. 7 times 3 to the second power, because you have two 3's. That would be your prime factorization, 7 times 3 to the second power. And if you actually work these results out, you'll get the original number you came up with. If I do 7 times 3 squared, of course I would do the 3 squared first. I'd end up with 7 times 9, which equals 63. So that's a way you can check your prime factorization to make sure you're right. See if you get the original number back when you do the math. Alright, we have 104. We're going to factor 104. Well, some greatest factors of that would be 52 and 2. Alright. 52 and 2. Can we do anything further with the 2? We cannot. It's a prime number. But we can certainly do something with the 52 here. 52, you got, well, 13 and 4 are factors. 13 and 4 would be factors of 52. We can't do anything further with the 13 because that's a prime number, just 1 in itself. But we can certainly do something with the 4. So we're going to have 4 breaks down into 2 times 2. Well, we can't break down the 2's any further. They're prime numbers. So your prime factorization is going to be, at the end of this tree, you'll have 13. You'd have 13 times 2 times 2 times 2. Or if you want to make it simpler, write 13 times 2 to the third. Because you have 2 times 2 times 2, that's 2 to the third. So the answer for this would be 13 times 2 to the third. That would be your prime factorization of 104. Alright, of course then we have 100. We can factor 100. I think everyone, including myself, is going to go for 10 and 10 as factors. 10 times 10. That works. Can we factor the 10s any further? We certainly can. We can have 10 breaks down into 2 and 5. So does that 10. It breaks down into 2 and 5. Can we factor the 2s or the 5s any further? No, they're both prime numbers. You can't factor any further. So your prime factorization is going to be 2 times 5 times 2 times 5. Which, we know we have 2 times 2. We have 2 twice. That would be 2 squared. Times, we have 5 times 5, well, that'd be 5 squared. So your prime factorization of 100 is going to be 2 squared times 5 squared. That's what that would break down into. So, good to know that about 100 is 2 squared times 5 squared for your prime factorization. So if you form the number trees like we're doing, it's easy. Alright, I think we've done numbers. Now, we're going to factor what's called monomials. What is a monomial? Well, as we get further in, like in Algebra 1, you'll learn about polynomials. Well, a monomial is a type of polynomial. It is a one-term variable equation. It's a one-term variable equation, or expression, however you want to say it. A one-term variable expression. I'll give you an example here. Let's say we have 14w, right? We got 14w, that's the only term in this expression, that's a monomial. Because you have a one-term variable expression, 14w is a monomial. We are going to do the prime factorization of this monomial. And of course, yeah, well, we'll go into binomials and things the other day, but a monomial, of course, a one-term variable expression. We're going to do the prime factorization for this one, 14w. Well, let's start with the tree here. You'll have 14 times w. Can we factor w any further? No, it's just going to be 1 in itself. We can't break down w any further. But we can certainly break down 14 further, which would be 2 times 7. At this point, can we break down 2 or 7 any further? We cannot. Those are prime numbers. So your prime factorization for this monomial is going to be 2 times 7 times w. So it would be 2 times 7 times w. It's a lot like, it is very much like doing it for regular numbers, only you have a variable. That's the only difference. It's a lot like doing it for numbers, only you have a variable. So that's something to keep in mind when doing these monomials. I got more. Alright, let's say we have 9t squared. We want to factor the monomial 9t squared. Well, we can break it down into 9 times t squared. Well, we can factor each one of them. Let's start with the 9, of course. We have 9 breaks down into 3 times 3, right? And then we have t squared, that'll break down into t times t. Well, we can't factor 3 or t anymore because they're both prime. You just have 1 in t or 1 in 3. So your prime factorization for this is going to be 3 times t times t. Which, if we want to get technical here, when we do the exponents, because you'll have 3 times 3, that's 3 squared. T times t, that's t squared. Your prime factorization is going to be 3 squared t squared. That would be your prime factorization for this number. Alright, let's do some more here. What if we got, good one, negative 7c squared. We have a negative number. Oh, what are we going to do? Well, let's break this down into negative 7 and then c squared. Well, the negative 7 we can do nothing with. That's a prime number. Negative 7 would just have 1 in itself. We leave negative 7 alone. But the c squared we can break down further. You would have c squared, which would be c times c. Now you can't break down the c's any further because the only factor would be c and 1. It'd be c and 1 for each one, so those are prime. So your prime factorization is negative 7 times c, which would equal negative 7 times c times c, that's c squared. So it's actually already its own prime factorization. It already is, but that's just to show you a breakdown of it. Alright. What do we got here? Alright, we got negative 25z cubed. We have negative 25z cubed. Well, we can break this down again into negative 25, and then we're going to have z cubed. Okay. Well, we have a negative, so the negative sign kind of just hangs out there. Factors of negative 25 are you'll have negative 5 times positive 5. So you have negative 5 times 5. That would be a factor. You can't break down the 5's any further. You're done with the negative 25 aspect of your prime factorization. So then we can break down z cubed, which will just give you z times z times z. That breaks down into z times z times z is z cubed. So your prime factorization is going to be negative 5 times 5 times z times z times z, which would just break down into negative 5 times 5. Then you have z times z times z. That'd be z cubed. We treat the negative 5 and positive 5 as different numbers, so that would be your prime factorization as negative 5 times z cubed. That would be your prime factorization of this number. Alright. What do we got here? We got 20 st. We have 20 st. So we can actually break this into 3 parts, because you have 20 times s times t. Well, s and t, we can't do anything with those. Those are already prime factored, because s, the only factor of that is going to be 1 in itself. Same with t, it would just be 1 in itself. We're done with that. Now, factors of 20, well, classic would be 4 and 5. Those would be classic factors of 20. Can we do anything with the 5? No, that's a prime number, but we could do something with 4. That would be 2 and 2. Can we factor the 2's any further? We certainly cannot, so your prime factorization is going to be 2 times 2 times 5 times s times t, which, when we go through and do exponents to figure out if we have any repeating factors, 2 times 2, well, 2 repeats twice, so that would be 2 to the second power times 5 times s times t. So that would be your prime factorization of 20st, would be 2 to the second power times 5 times s times t. All right. All right, we have negative 38 m n p. Negative 38 MNP. Well, we have 4 things being multiplied here, so we can break this down into 4 parts. We can actually break this down into 4 parts. You'll have the negative 38 times the n times the n times the p. So if we're doing this negative 38 times m times n times p, we can break these down into 4 separate multiples. Well, immediately we're done with m, n, and p. They're already prime factored. The only factors of them are 1 in itself. But we can deal more with the negative 38. Negative 38 factors of that could be negative 19 and positive 2. That would give you negative 38. At which point now, can we do anything further with negative 19 or 2? No, they're both prime numbers. There's no factors besides 1 in itself that are going to give you those numbers. So therefore, they're prime factored. So your prime factorization is going to be negative 19 times positive 2 times m times n times p. That would be your prime factorization for this, is negative 19 times 2 times m times n times p. And it's good that you're seeing how the negative numbers work with these factorizations. All right. Oh, good one. We have 28x squared y. We have 28x squared y. Well, this could be a 3-parter because you have 28 times x squared times y. Let's start with the y. Can you factor y any further? No. It would just be a factor of 1 itself. That's done. How about x squared? Can we factor x squared any further? We sure can. It would just be x and x. Can we factor 28 any further? We sure can. You could do 4 and 7. Well, the x's don't factor any further. They're each their own prime factor. You just have 1 times x for each one. You couldn't do that any further. You can't factor 7 any further because it's a prime number. It's just 1 and 7 for the factors. But we could factor 4. That comes down to 2 and 2. And we can't factor the 2's any further, so therefore we have our prime factorization. Start from the left, you'll have 2 times 2, 2 times 2 times 7 times x. You have x times y. So, in order to get a proper prime factorization, you're going to want to look for multiples of the same number. We have 2 times 2, which would make that 2 squared. Then you just have times 7. Then you have x times x, which is x squared. Then you just have times y. So your prime factorization for 28x squared y is 2 squared times 7 times x squared times y. That would be your prime factorization. Got a little bit more here. I believe this is very important, especially when we go to factor, that know how to do prime factorizations. Alright, we have 21 GH cubed. 21 GH cubed. So we have 21, we have G and H cubed. So that tells us we have 3 things being multiplied. We got 21, we got G, then we have H cubed. We can break that down into 3 parts. 21 times G times H cubed. Well, let's start. Can we factor 21? We sure can. You'd have 3 and 7. Well, we can't factor 3 and 7 any further since they're prime numbers, so we're done there. Can we factor g? No, it would just be 1 in itself, so g's already factored. But how about h cubed? Sure, it'd actually factor 3 ways. It would be h times h times h. H times h times h would make it h cubed. Now we can't factor the h's any further since they're down to just h. It would just be 1 in itself. So your prime factorization would start out looking like 3 times 7 times g times h times h times h, which 3 times 7 would stay left alone. So would the g, 3 times 7 times g. Now h, we have repeating factors of h, so you'd have h times h times h. That would be h to the third power. So your prime factorization of this is going to be 3 times 7 times g times h to the third power. That would be your prime factorization. Let's see, I'd like to do at least 2 more. No, I think we can do the 4 more. We could do the 4 more. 13q squared r squared. So that tells us we have 3 things being multiplied. We have 13 times q squared times r squared. So let's break that down here. You have 13, then you have q squared, then you have r squared. Well, 13 factors no further. 13 will factor no further because it's a prime number. But q squared can factor into q times q. R squared can factor into r times r. Well, can we factor the q's or r's any further? We certainly can't. You just get a factor of 1 in itself. So your prime factorization is going to be 13 times q times q times r times r. Some teachers like the answer like that, by the way. When you factor completely out, some teachers do like that answer. But being technical with prime factorization, if you have repeating multiples, it's best to put it in power form. So you'll have 13 times q, that's q to the second power, times, then you have r times r, well, that's r to the second power. So that would be your prime factorization. It turns out it was already in prime factored form. 13 times q squared times r squared. Alright. We have 64 n cubed. So we have 64 n to the third. How are we going to do the prime factorization of that? Well, we have 2 things being multiplied, 64, then the n cubed. So we can break that down into 64 and then n cubed. Okay, well let's start with 64. Can we factor that? Sure can. Classic factors are 8 times 8. Can we factor the 8s any further? We sure can. You'll have 2 times 4. Each 8 has factors of 2 times 4. Well, we can't factor the 2's any further, but we could certainly factor the 4's. 4 breaks down into 2 times 2. This 4 also breaks down into 2 times 2. Okay, so we factored out 64 completely because we can't factor out the 2's anymore. We can factor n cubed. That's just n multiplied by itself 3 times. So we can't factor the n's any further. So we have n times n times n, which would make n cubed. So your prime factorization would start like this. You'd have 2 times 2 times 2 times 2 times 2 times 2 times n times n times n. Yikes, we got a lot of 2's there. So we get 2 times 2 times 2 times 2 times 2 times 2 times n times n times n. Well, there's got to be a simpler way to write this. Well, there is. We have repeating 2's. So we have 1, 2, 3, 4, 5, 6 2's. So you can write that as 2 to the 6th power. And then you have n times n times n. That would be n to the 3rd power. So your prime factorization for this is going to be 2 to the 6th times n to the 3rd power. That would be your prime factorization of 64n cubed. Alright. Yeah, that is a lot of 2's there. We got 2 more. We do have 2 more, then we're done. We have negative 75 AB squared. Negative 75 AB squared. So that tells us we have 3 things. Negative 75 times A times B squared. Okay. Let's start with factoring negative 75. Classic factor we're all going to think of is negative 25 and 3. Well, we sure as heck can't factor the 3 any further. That's a prime number. But we can factor negative 25. You would get negative 5 and positive 5 as factors, which we sure can't factor any further. Both negative 5 and positive 5 are prime numbers, so we can't factor those any further. Can we factor A? No, it's just 1 in itself for a factor. It's prime. Can we factor B squared? We can. That would just be B times B. At which point we can't factor the B's any further. So your prime factorization is going to start like this. You'll have negative 5 times positive 5 times 3 times A times B times B. Okay? Which, for your prime factorization, negative 5 and positive 5 are 2 different numbers. So you'll still keep negative 5 times positive 5 times 3 times A. But you have B times B. That would be to the 2nd power. Times B to the 2nd power. So your prime factorization is negative 5 times 3 times A times B to the 2nd power. Alright, I got one more. Alright, we got negative 120 r squared s t cubed. Yeah, that one looks like a doozy. We have negative 120 r squared s t cubed. So that tells us we have 4 things we're multiplying. Negative 120. We have negative 120. We have r squared. We have s. Then we have t cubed. So we broke these 4 things down into individual multiples. Let's start with negative 120. Can we do negative 120? Are there any factors that we can do for that? Well, why not start with negative 2 times 60? That's as good as any place to start. Well, negative 2 is already a prime number. We can't factor that any further. But we can do 60. Well, how about 15 or 4 and 15? We could factor 4 and 15 out of 60, in which 4 and 15 actually could both be factored further. 4 factors into 2 and 2, and then 15 factors into 3 and 5. Well, 2 times 2, that's those can't factor any further. 2 is a prime number. Same with 3, same with 5. So we've done and completely factored the negative 120. Can we factor r squared? We can. That's just r times r. We can't factor the r's any further because they'd just be 1 in itself. S, well, we can't factor s any further. The factor is 1 itself, but we could factor t cubed. We could definitely factor that. You would just have t times t times t would give you t to the third power. So your prime factorization is going to look something like this. You'll start with negative 2 times 2 times 2 times 3 times 5 times r times r times s, wow, times t times t times t. This is why we often choose to write multiples in exponent form, because you can get a really long result of its prime factorization. Well, what I would do next, go through, look for multiples of the same number. Negative 2 is on its own. That stands on its own. But you have 2 times 2, which would be 2 squared. So you have negative 2 times 2 squared times 3 times 5. R times r, that's r to the second power. Then you have s by itself. Then you have t times t times t, that's t to the third power. So your prime factorization is going to be negative 2 times 2 squared times 3 times 5 times r to the second power times s times t to the third power. So, biggest thing with prime factorization is you want to factor numbers down until you get them down to a product of prime numbers. If you have repeating numbers, you can make exponents out of that number, which is what you would do, like we have here. If you have a negative number in there, the negative stands by itself. So that negative 2 does not count as part of 2 squared. It doesn't count to make it 2 cubed at all, because negative 2 is its own number. So basically that's all there is to prime factorization. The next lesson we're going to find greatest common factors of numbers. So stay tuned for that, and I hope everyone has a good day. Take care.